Now let us look at what is called as a Dirac Delta function. This is a very important function which is very useful in solving many problems, and in fact it acts as a bridge between Fourier series and Fourier transforms. So let us look at a Dirac Delta function today completely, and we also look at some of its applications and how useful it is. We will understand at the end of this session. Okay, let us start with the Dirac Delta function. So what is the Dirac Delta function? It is denoted by the letter delta of t. So it is defined as having 0 amplitude everywhere except at t is equal to 0. So let us see this here. Okay, let us say a delta function. Okay, we are using the letter delta of t for this. So it says that this is my delta of t. If you look at this, this is existing only at t is equal to 0. It does not exist when t is not equal to 0. So how can I write the equation for this? The equation can be written as delta of t is 0 when t is not equal to 0. That means when t is not equal to 0, it is like this. Otherwise, we can also write like this. Delta of t will have a value, let us say unit delta function, t is equal to 0 and 0 elsewhere. Okay. So this is a delta function for us. So as we see here, it is defined as having 0 amplitude everywhere except t is 0, as shown in the board. We have seen that. Then the amplitude is infinitely large such that it contains unit area under its curve. That means what? When I integrate this from infinity to plus infinity, delta of t dt, then this is equal to 1. That is, when I integrate between minus infinity plus infinity, that is, we are calculating the area under the curve. So we have to get this one. This is possible only if this amplitude is infinite. Then let us see some properties of delta function. The first property is called as a shifting property. So what does it say? It says integral minus infinity to plus infinity g of t, delta of t dt is equal to g of 0. So what does it mean? So what does the shifting property says? It says I am integrating between minus infinity to plus infinity a function g of t and delta of t dt, then this value is equal to g of 0. That means what are we doing here? We are shifting. That means we are selecting or filtering only one value of the given function g of t. How I am doing that? When I integrate this, the multiplication, the product of g of t delta of t, I am getting a value that is equal to g of 0. That means we are able to select or filter only one particular value of the given function. So this we can extend it. We can also say this as minus infinity plus infinity g of t, and I am multiplying this with the g of t minus t naught delta t, then the answer will be g of t naught. Okay. That means now I am able to select or shift or filter a value of g of t at t is equal to t0. So that means here what is that we are doing? We are taking the delta function at t is equal to 0, and I am taking a delta function at t is equal to t0. So this is delta of t minus t naught, and this is delta of t. So whatever is the value of g of t at this particular value will be the function here. So this is the shifting property. Okay, you can extend this like this, and then you should appreciate the fact that shifting means a sort of selection or some filtering action is happening where a single component of your given signal is we are able to take it out. This is the importance of a shifting property. If you look at this shifting property, it almost resembles convolution. Here earlier if you have seen the properties of convolution, we said minus infinity plus infinity g of t convolved with delta of t will be g of t itself. So that is a convolution property. Okay. Let us look at another property called as replication property of delta function. So what does replication property say? It says as follows: the convolution of any function with delta function leaves that function unchanged. That means when I convolve g of t with delta of t, the result will be g of t. That means we are not changing the value of the given signal g of t. This is called as a replication property. Let us see another Fourier transform of delta of t. Let us see what is the Fourier transform of delta of t. Now, delta of t, the Fourier transform of delta of t will be equal to 1. That means, I have a Fourier transform, this is my delta of t, okay. This will have a Fourier transform whose value is 1, and you see this is extending from minus infinity to plus infinity. So, this is the Fourier transform of a delta function. Now, let us see some applications of delta functions. What are the applications of delta functions? We see one of them is, the first one is called as a DC signal, the second is a complex exponential function, the third one is a sinusoidal function, the next one is a unit step function, and finally we have a signum functions. We will see what are the applications of delta in this applications. The first one, let us see what is called as a DC signal. Okay, applications of delta functions. Okay, the first one is a DC signal. Okay, how does a DC signal look like? This is our DC signal. Okay, let us say this is my G of t. This is a DC signal. We want to know what is the frequency spectrum or frequency of this. So, when we look at this type of function, we should remember the earlier what we have seen, what is the Fourier transform of delta function. So, what is the Fourier transform of a delta function? Delta of t will have a Fourier transform which is equal to 1. Now, this is 1 for us. Okay. So, this is what is given in time domain. So, apply a duality property, and knowing the fact the delta function is an even function. So, what will be the Fourier transform of this? The Fourier transform will be a delta function in the frequency domain. So, what is that now? So, I will get a delta function here. This is my delta f and this is the frequency spectrum. So, this is the Fourier transform of a DC signal. So, it says that DC signal will have a Fourier transform which is a delta function which is existing at f is equal to 0. So, here a DC signal will have a delta function at f is equal to 0. So, what does it mean? If you know, we have seen what is the formula for Fourier transform, isn't it? So, here minus infinity to plus infinity, what is the value here of a g of t here? 1, isn't it? So, 1 into e to the power of minus j2 pi f t dt will give me the Fourier, that is the Fourier transform g of f, that is nothing but equal to delta f. That means integral minus infinity to plus infinity e to the power of minus j2 pi f t dt will have a Fourier transform which is equal to delta f f. This is a very important deduction we have made from this. So, whenever e to the power of minus j2 pi f t dt is integral is taken from plus infinity, minus infinity to plus infinity, it will give me a function which is equal to delta of f. Now, let us see the second application of delta function. Yeah, let us see the second application, that is complex exponential function. Okay. Let us look at the second one, that is a complex exponential functions. So, we know just now we have seen this delta of f is equal to having a Fourier transform or inverse Fourier transform fund, that is one will have a Fourier transform of delta f. Now, if this is multiplied by a fraction, let us say this is exponential of j2 pi fct, okay, then what will be the Fourier transform for this? So, if you look at the frequency shifting property, what does the frequency shifting property says? e to the power of j2 pi fct g of t will have a Fourier transform which is equal to g of f minus fc. Okay, f minus fc here. So now apply this here. So this is 1. Now this is multiplied by exponential function which is e to the power of j2 pi fct. So what will be the Fourier transform of this? The Fourier transform, applying the Fourier frequency translation property, then I can have this as delta of f minus fc. It means that the Fourier transform of an exponential function will be equal to delta function which is shifted to that frequency which is equal to the frequency here. Suppose if this is minus j2 pi fct, okay, it will have a delta function which is delta of f plus fc. That means a complex exponential function Fourier transform will be a delta function existing at that particular frequency given by the exponential component here. So, you will have if it is e to the power of j2 pi fc, it will be delta f minus fc, and if it is e to the power of minus j2 pi fct, it will be delta of f plus fc. So, this is the second application of your delta function. Now, let us look at the third application, that is about a sinusoidal function. Sinusoidal functions. Okay. There are two types of sinusoidal functions as we all know. So, let us look at first a cosine function. Okay, a cosine function can be written in terms of an exponential functions. So, this I can write as half of e to the power of j2 pi fct my plus e to the power of minus j2 pi fct. So, we have seen earlier that exponential function in time domain will have a Fourier transform equal to a delta function existing at this frequency. So, I can write this in terms of Fourier transform. So, what will be the Fourier transform of this? So, this will be half of, what is this? This is equal to delta of f minus fc, plus what is this? This will be delta of f plus fc. That means a cosine function in frequency domain will be consisting of two delta functions, one existing at f is equal to fc, the other is existing at f is equal to minus fc, scaled by a factor 1 by 2. So, a cosine function is represented in terms of a delta function in frequency domain. Let us draw this now. So, what is the cosine function? Cosine function looks like this. Some function like this. This is in time domain. The frequency domain, it will look like this. This is fc and this is minus fc. So, you will have a delta function here. This is g of f, and you have another delta function here. So, this is in the frequency domain. So, cosine function in time domain is translated into two delta functions existing at a plus fc and minus fc for a function which is cos 2 pi fct. So, this is the Fourier transform in the frequency domain. This is the, I repeat, this is the Fourier transform of a cosine function. Similarly, let us look at a sinusoidal function. Second, that is sinusoidal function. Sinusoidal function, that is sine 2 pi fct. We know this can be written in terms of exponential function. So, this will be e to the power of j2 pi fct minus e to the power of minus j2 pi fc t. So, again let us take the Fourier transform for this. So, Fourier transform of this sine 2 pi fct function will be, this will be the Fourier transform of this will be equal to delta of f minus fc minus delta of f plus fc. So, again this also is a Fourier transform here is also equal to two delta components existing at f is equal to fc existing at f is equal to fc and the other one existing at f is equal to minus fc. Of course, there is a scaling factor of 2j. So, let us draw the frequency spectrum for this. Let us draw the frequency spectrum for this. So, this looks like this. Okay, this is j g by g of f. Let us take this here. So, this is fc. There is a Fourier transform here, and this is minus fc. There is another Fourier transform here. Okay. So, this is the Fourier transform or a spectrum of a sinusoidal function whose frequency domain is equal to 1 by 2j. I repeat, whose Fourier transform is equal to 1 by 2j delta of f minus fc minus of delta of f plus fc. So, this is how it looks like. So, when I apply delta function to a sinusoidal functions, again we can represent a cosine function in terms of a delta function. We can also represent a sinusoidal function in terms of the delta functions. Let us see the other application, that is unit step function. Okay. So, let us look at this now. So, what is the Fourier transform of delta of t? That is 1, and the integration property, Fourier transform of integration property says, let us also use that here, minus infinity plus infinity g of tau d tau will be equal to 1 by j 2 pi f plus g of 0 by 2 delta of f. This is the Fourier transform. When I time integration property, this is what you will get. Now, for us, what is g of tau here? Delta. So, if we take this as minus infinity plus t delta of tau d tau, this is equal to 1 by j 2 pi f, okay, plus 1 by 2 delta of f. Okay. So, when you look at this function, this will take 3 values. For all values of t which is negative, this will take a value which is equal to 0. At t is equal to 0, this will be equal to half, and for t greater than 0, that is, it will become 1 here. So, if you look at this, for all negative values of t, this function is taking a value of 0. For all values which is t greater than 1, it will become 1, and for t is equal to 0, this will become half. This integral takes 3 values. When t is negative, the value is 0. When t is equal to 0, the value is half. When t is equal to greater than, it is a positive values of t, then that is greater than 0, its value will become 1. If you look at this, all this, so these are the values of a unit step function, is it not? So, this is we can represent in terms of a unit step function. So, unit step function is this, okay, that is nothing but, now what is u of t for us then? U of t is nothing but minus in plus t delta of tau d tau will give me a unit step function. Okay. So, now let us write this here. What is unit step function now? I can write this as unit step function is equal to, we have just seen that will be equal to 1 by j 2 pi f plus delta f by 2. So, this is the unit step function u of t is equal to 1 by j 2 pi f plus delta f by 2. Let us draw the time domain representation and the frequency domain representation here. So, u of t, as you are aware, this is a positive function. So, this will be like this. This is u of t for us. This is 1 and this is t. Okay. It will frequency domain spectrum will be like this. Okay. There exists a delta function at 0. So, we have put a delta function here, and then 1 by j 2 pi f is something like this. So, this is the frequency domain representation of a unit step function. So, if you look at this clearly, unit step function will have a delta function existing at t is equal to 0. That is the importance of a unit step function here. Whenever unit step function, you try to you take a frequency domain representation of it. In the Fourier transform of the frequency domain representation of the unit step function, it will invariably have a delta function at 0, t is equal to 0. So, this is the unit step function significance. Let us see the fifth application, that is a signum function. Okay. What is the signum function? We are using the letter signum SGN, okay, of t. This is signum function. This will have 3 values. It will be 1 when t is greater than 0, 0 when t is equal to 0, and minus 1 when t is less than 0. Now, this is the signum function. So, how does it look like? Now, this is how a signum function looks like. This is the signum, this is plus 1, t is greater than 0. So, this is 0, so there is no value, and minus 1. This is the time domain representation. This is signum of t. So, signum of t has taking 3 values as you see. When t is greater than 0, this is 1, t is equal to this is 0, t is equal to 0, this is 0, and then here for t less than 0, this is minus 1. So, a signum function can be represented in terms of a unit step function. So, how is that? I can write this as 2 u of t minus 1, is it not? 2 of u of t minus 1. So, I want to write down in terms of frequency domain. Earlier we have seen what is u of t equal to? This is the frequency, isn't it? 1 by j 2 pi f plus delta f by 2, is it not? So, let us bring that here. So, this will be equal to 2 by j 2 pi f plus delta f by 2 into 2 minus 1. So, this is equal to 1 by j pi f. This is equal to 1 by j pi f. That means, a signum of t will have a Fourier transform which is 1 by j pi f. So, what will be the Fourier transform here? So, that will look like this, okay, in the frequency domain. So, that is the frequency domain representation of a signum function. Now, I will apply a duality property to this. This is one result which is very good. We got this here, and then if I apply a duality property to this, then I will get this as 1 by pi t will have a frequency domain representation of minus signum of f. Okay. So, this is the signum function which is having a Fourier transform 1 by j pi f. Apply a duality property to this, then 1 by pi t will have a Fourier transform as minus j signum of f. That means, signum of f again is signum of f will be simple here. For f, now it is f here. So, it will be plus 1 for f greater than 0 and minus 1 for f greater than 0, of course, with a certain signification, certain multiplication factor of minus j. Okay. So, this is the signum function for us. Now, let us see Fourier transform of periodic signals here. A periodic signal can be represented in terms of Fourier transforms, provided that this transform is permitted to include delta functions. Okay. The Fourier transform of a periodic signal consists of delta functions occurring at integer multiples of the fundamental frequency 1 by t naught, including the origin. So, generally the general perception is whenever you have a periodic signal, we use Fourier series for that. So, when I want to use a Fourier transform for a periodic signal, what is that I have to do? Whenever you want to apply Fourier transform to a periodic signal, there must be a provision for us to include delta functions in your Fourier transform. So, whenever you have a delta function, this delta function occurs at regular intervals of time. Let us say 1 by t naught, 2 by t naught, 3 by t naught. So, they are occurring very regularly. That includes the origin also. That is what this function. A periodic signal can be represented in terms of Fourier transform, provided that this transform is permitted to include delta functions also. The Fourier transform of periodic signal consists of delta functions occurring at integer multiples of the fundamental frequency 1 by T naught, including the origin. So, let us just discuss this again. So, whenever I want to calculate the Fourier transform of a periodic signal, then there is a provision for the Fourier transform to have a delta function in it. So, if delta functions are present in the Fourier transform. So, where are these delta functions present? They are present the integer multiples of the fundamental frequency, that is 1 by T naught. That also includes the origin. Let us see this. How does this look like? Pictorially, it looks like this. Okay, now this is the Fourier transform F domain, and this is the origin. Okay. So, there is a delta function which is occurring at origin. There is again a delta function which is occurring at 1 by T naught. There is again a delta function which is occurring at 2 by T naught. Similarly, there is a delta function which is existing at minus 1 by T naught. Then there is a delta function existing at minus 2 by T naught, minus 3 by T naught, okay, and plus 3 by T naught, okay, like that. So, you will have lot of delta functions. They are existing from at all multiples of the fundamental frequency 1 by T naught, 2 by T naught, 3 by T naught, like that they exist. When you look at this, these are representing the comb. That is why this is called as a Dirac comb function. That means, when I take a periodic waveform and we take a transform of it with the provision that the transform should contain delta functions, and these delta functions exist at every 1 by T naught, 1 by T naught, 2 by T naught, 3 by T naught, plus or minus, including origin. So, they look like a comb. That is why this is called as a Dirac comb function.